So here's our quick Unit 2 review video. I highly recommend that you watch this, think about it before you start the unit exam. So one of the things that we missed on the review quiz was electron configuration. So that idea of where electrons are in energy levels, configuration, where they are in energy levels and those orbitals and all those pieces and parts. So we know that there are energy levels, and we count them as rows headed down the periodic table. So energy level number 1, hydrogen and helium have electrons only in energy level number 1. These guys valence electrons are in energy level number 2. This row of atoms have valence electrons in energy level number 3, and so on. So there are different sublevels in each energy level. So we show them with letters, so S, P, D, and F. Energy level 1 has only an S sublevel. Energy level number 2 has an S and a P. 3 has an SP and a D. 4 has SPD and F, and so on and so forth. Energy level 1 with its one sublevel S has only one orbital, and each orbital, or cloud-like structures around the nucleus of the atom where we find electrons, each orbital has space for only 2 electrons. So an S sublevel has only one orbital, has a maximum of 2 electrons. And we can see that in energy level number 1 that has only an S sublevel, and there's space for only 2 electrons. When we look at the P, now we have space for 3 orbitals. Each orbital can hold 2 electrons. So 2 times 3 is 6 total electrons. And this, our P block, we can see is 6 elements wide. 1, 2, 3, 4, 5, 6, because there's space for 6 electrons in each P sublevel because there are 3 orbitals. So I said just a second ago that energy level number 2 has S and P. This is the 2S sublevel. This is the 2P sublevel. Energy level 3 has SP and D. The D sublevel has space for 5 orbitals. 2 times 5 is 10 total electrons. And we see those 10 right here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the 10 electron spaces that are available in those D sublevels. So I said that energy level number 3 has space for SP and D, except there's no D here in energy level number 3. Remember how we talked about how the energy levels start getting really close to each other and they start to overlap? So this is where that overlapping starts. So this is 3S1 and this is 3S2. This is 3D1. So this is the 3D sublevel. This is 4D sublevel. F is way down here. The F sublevel has 7 orbitals. 2 times 7 is 14 total electrons. What's kind of weird is that we chunk out these guys and put them here. So we actually have 15 elements along the F block, but these guys really belong here and here, which leaves us with 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 7 orbitals, 2 times 7 is 14 total electrons. This is our S block. This is our P block, the D block, and the F block. We can use that information to write electron configurations of our elements. Helium, we look at the periodic table, it's element number 2. That means it has 2 electrons. We're going to always start at the lowest energy possible first. Lowest energy level available is 1s. So we're going to draw 2 electrons in the 1s orbital because it's the lowest energy first. So helium's electron configuration is 1s2. Boron has 5 electrons. I'm going to reset our Aufbau diagram. Let's pick a fun new color. So boron's 5 electrons are going to go 1, 2. This guy is full, only space for 2 electrons. The next 2, 3, and 4. 1, 2, 3, 4. I have 1 more electron. It's going to go up here in the 2p. So boron's electron configuration, 1s2, 2s2, 2p1. Carbon has 6 electrons. I'm going to erase and start over. again. Carbon 6 electrons. 1, 2, 3, 4, 5, 6. We're going to write carbon's electron configuration 1s2 because there's 1, 2 electrons in the 1s orbital. 2s2 because there's 1, 2 electrons in the 2s orbital. And 2p2 because there's 1, 2 electrons in the 2p orbital. Sodium has 11 electrons. I'm not going to erase, I'm just going to add on. So we've got 11 electrons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so sodium's electron configuration is going to be 1s2, 2s2, 2p6, 3s1, because there's 1, 2 in the 1s, 1, 2 in the 2s, 2, 4, 6, 6 in the 2p, 2p6, 1 electron in the 3s orbital, 3s1. Silicon is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so its electron configuration is going to be 1s2, 2s2, 2p6, 3s2, 3p2. Argon has 18 electrons. 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17, 18. Argon's electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6. Hopefully that helps make electron configuration make a little more sense. Now let's talk about the energy that is released when electrons jump back and forth between those energy levels. So we measure this energy in waves, a couple different pieces of waves that we need to know about. The distance between two corresponding pieces of a wave is known as the wavelength. We use the Greek letter lambda to represent a wavelength. This guy has a short wavelength. This guy has a long wavelength. We can also measure frequency of waves. This guy has high frequency because there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 waves are passing, and so we're going to call that frequency 12 hertz. Here I only have 1, 2, 3, 4. So this guy's a little bit slower. He has only 4 hertz of energy. And so that lower frequency is going to be associated with a longer wavelength, and it's also associated with lower energy. Because you can imagine that drawing this guy doesn't take as much energy as drawing this guy. Way more energy in that high frequency, short wavelength. Lower energy, higher energy. So higher frequency, higher energy, lower frequency, lower energy, higher frequency, shorter wavelength, lower frequency, longer wavelength. And then we can show some graphs to represent the relationships between these. So if I put energy on the y-axis, frequency on the x-axis, when one is low, the other one is also low. That would be like here. When one is high, when the frequency is high, the energy is also high. And so that would be like here on the graph. And so we can draw a direct relationship between energy and frequency. They go up together. The opposite happens if I look at energy and wavelength. If I have high energy, I have a small wavelength. So when energy is high up here, the wavelength is small, like here. And then vice versa, if I have a longer wavelength, that wavelength is big, I'm going to graph it out here, the energy is going to be low. And so this is an inverse relationship, and it's going to look a little bit like that. So energy frequency direct relationship, energy wavelength inverse relationship. We can do some calculations with frequency, wavelength, and energy. These three formulae are on the top of your periodic table, that very first page of all of those formulae that you have. So I look here and I see that red light has a wavelength. What's its frequency? I'm going to find the formula that puts together wavelength and frequency, and that is this guy, frequency and wavelength. Speed of light equals frequency times wavelength. So remember that speed of light is a constant equal to 3.00 times 10 to the 8th meters per second. So I'm going to plug that in for C. You don't have to memorize that. That's on the back of the first piece of paper that is stapled to your periodic table. So where you have these formulae, the back of that same piece of paper, you have that constant. Speed of light is 3.00 times 10 to the 8th meters per second. So I'm going to plug that in for C. 3.00 times 10 to the 8th meters per second. And that's going to equal frequency times wavelength. So I'm going to put frequency in here. I don't know what it is yet, and I'm going to plug in wavelength for wavelength, except here's a problem. I have nanometers, I have meters. That's not a match. I need to turn my 720 nanometers into meters because this meters and those meters need to match. So we're going to do a quick review of metric conversions. So 720 nanometers. Remember how many nanometers are in a meter? How many nanometers are in a meter? There are one, not 1,000, not a million, but 1,000,000,000, 10 to the 9th nanometers in 1 meter. And so I'm going to put nanometers on the bottom, nanometers on top, and bottom cancel out. 720 divided by 10 to the 9. I'm going to put that into my calculator. 720 divided by 10 to the 9th power is going to give me 7.2 times 10 to the minus 7 meters. Now that I have meters, I can plug that in. 7.2 times 10 to the minus 7 meters. To solve for frequency, I'm going to divide both sides by 7.2 times 10 to the minus 7 meters. That cancels out on the other side, 7.2 times 10 to the minus 7 meters. When I divide in scientific notation with my calculator, I need to make sure that the denominator is in parentheses or I'm going to get the wrong answer. So 3.00 times 10 to the 8th power divided by 7.2 times 10 to the negative 7th power. I'm going to put that in parentheses, and my answer is going to be 4.166666. A lot of sixes. E14. So let's check our sig figs. We get to keep 2, not 3. 2 is fewer than 3. So my frequency is going to be 4.2. Remember that E14 means times 10 to the 14th. Frequency's unit label is hertz. 4.2 times 10 to the 14th hertz is going to be our answer here. So this is a similar question. I've got joules of energy. I'm looking for frequency. I need to find the formula that puts together energy and frequency. It's this one, where energy is equal to Planck's constant times frequency. I can find Planck's constant on my list of constants and conversions very close to speed of light. So Planck's constant is h, and it's equal to 6.63 times 10 to the negative 34 joule seconds. So I'm going to use my E equals hf. Energy equals Planck's constant times frequency. Plug in my energy for energy, 5.1 times 10 to the minus 19 joules. Set that equal to Planck's constant h, 6.63 times 10 to the minus 34 joules seconds. That's multiplied by F. I don't know what F is. That's what I'm trying to find. Divide both sides by 6.63 times 10 to the minus 34 joules seconds. That cancels out. We're left with just F. On the other side, we need to also divide by 6.63 times 10 to the minus 34 joules seconds. Joules divided by joules cancels out. I have seconds in the denominator. That's hertz. So my formula is going to be hertz, my unit label is going to be hertz. 5.1 times 10 to the negative 19 divided by 6.63 times 10 to the negative 34 gives me 7.7 times 10 to the 14th hertz. So just a quick check on exponent reasonability. 14 on your exponent for hertz is good. Negative 19 on your exponent for joules is good. Wavelength, you're usually going to have 10 to the minus 7 meters is good. So check that reasonability, make sure that things are looking good. Definitely make sure that you are using parentheses in the denominator when you are dividing in scientific notation. All right, atomic radius. I know the picture's a little bit blurry, but we're looking at sizes. So sodium is bigger than magnesium, even though magnesium has more mass. And the reason is this. These guys both have 3 energy levels of electrons. Sodium has 11 protons in the nucleus pulling on those 3 energy levels, whereas magnesium has 12 protons pulling on 3 energy levels of electrons. A nucleus with 12 protons is a stronger magnet and is going to pull those energy levels in closer. And so magnesium's radius is going to be smaller. Those 12 protons compared to only 11 protons, 12 protons is a stronger magnet, pulls the electrons in a little bit closer. So I've got 11 is going to be a little bit bigger than 12. How about 19? 19 protons in a potassium nucleus ought to be smaller yet. But wait, it's bigger. That doesn't make any sense, except it does, because these guys have 4 energy levels. And so these guys have to pull on only 3 energy levels. They have 4 energy levels of electrons. Every time we add an extra energy level, the atom is going to get bigger. So 3 energy levels is going to be smaller than 4 energy levels, but 19 protons versus 20 protons. 20 protons is going to pull those 4 energy levels closer than only 19 protons. And so calcium will be smaller than potassium, but calcium will be bigger than magnesium because he has 4 energy levels and he only has 3. So remember that when we're going across the periodic table, going across a period, they're getting smaller. The atoms are getting smaller because there are more protons pulling on the same number of energy levels. But when we go down a group, they're getting bigger because there are more energy levels that have to be pulled on. More energy levels is bigger, but more protons is smaller. So remember that average atomic mass, there are 3 steps you want to follow. Step number 1, turn your percents into decimals. 79.0% is 0.790 as a decimal. 10% is 0.100 as a decimal. 11% is 0.110 as a decimal. That's step number 1. Step number 2, you're going to multiply your decimal by the mass. And sometimes you're given a decimal you're given a mass. Sometimes you have to know to find it in the isotopic notation. So these are the masses of these 3 isotopes of magnesium. So we're going to do 24 times 0.790, 24 times 0.790 on my calculator is 18.96. 25 times 0.100 is my drawing tablet is acting all kinds of funky with those weird extra lines. Sorry about that. And then 26 for that last isotope, 26 times 0.110 is going to give us 2.86. 26 times 0.110, 2.86. 25 times 0.100, 2.5. Last step, step number 3, you're going to add those 3 pieces together. So 18.96 plus 2.5 plus 2.86 on the calculator gives us 24.32. This is the average atomic mass of magnesium. All right, so we talked a little bit about radioactivity in this unit. Some uses of radioactivity to know. Energy production is definitely a use of radioactivity. We can use radioactivity in our smoke detectors. We use it, of course, in medicine, in diagnostic, and in treatment. We can use it to find leaks in oil, so we can add a radioactive isotope to the pipe, and then we can figure out where the leak is with the Geiger counter. And then, of course, we use radioactivity in weaponry as well. So some of us on the review quiz talked about radiation being used as chemotherapy. Yes and no. Chemotherapy and radiation both have a similar goal in that they're both trying to kill cancer cells. Chemotherapy does it with chemicals. So these are medicines, chemicals that are being injected into the patient's bloodstream. Those chemicals are going to slow down mitosis so that the cancer cells cannot reproduce themselves quite as quickly. Radiation therapy, we're using that radioactivity from some radioactive isotopes. It's being shot at wherever the cancer is and hoping to break the DNA molecules in the cancer cells so that, again, the cancer cells die. So radiation therapy versus chemotherapy, similar, but radiation is not used in chemotherapy, only in radiation therapy. All right, last 2 little pieces. We're going to look at the alpha decay and beta decay of these 2 radioactive isotopes. So this is plutonium. Plutonium is element number 94. It has a mass of 239. I know that because it says right there, That's our mass number. Plutonium on the periodic table is number 92. It's going to go through, 94. It's going to go through alpha decay. Alpha decay is a helium nucleus being released from the radioactive atom. So we're going to send this helium nucleus out of this plutonium atom. So I've got plutonium turning into this alpha particle. This guy is the alpha particle. Sometimes we show it with the Greek lowercase letter a. And then we need to figure out what's left over when this guy pops out. So what we do is we're going to add the numbers on the bottom. The arrow is like our equals sign. So 94 is going to equal 2 plus something. 94 equals 2 plus 92. Same thing on the top. 239 is going to equal 4 plus something. That is 235. 239 is equal to 4 plus 235. 94 is equal to 2 plus 92. Element number 92 is uranium. So when plutonium goes through alpha decay, an alpha particle is released. What's left over is uranium-235. Beta decay of carbon-14. So again, we're going to put that radioactive isotope to start. I'm putting a 6 on the bottom because carbon is element number 6. So carbon-14, the mass is 14, 6 protons. The atomic number is 6. It's going to go through beta decay. Beta decay is an electron. An electron is going to pop out of the nucleus. That's weird. There are no electrons in the nucleus. Well, here's the deal. One of the neutrons in the nucleus of this carbon-14 atom is going to turn into a proton and an electron. The electron flies out of the nucleus. So that electron pops out, and then what's left over is this. Again, we're going to set tops and bottoms equal to each other on each side of the arrow. 6 is equal to -1 plus 7. -1 plus 7 is equal to 6. And then on the top, 14 is equal to 0 plus 14. 14 is equal to 0 plus 14. 6 is equal to -1 plus 7. Element number 7 is nitrogen. So the beta decay of carbon-14, the beta decay, here's my beta particle. The beta decay of carbon-14 results in a beta particle or an electron and nitrogen-14. And that's the end of our review. Hopefully this is a help. Good luck on your test.